Yo, you know who it is. It's your boy Algebra coming to you live and direct from the studio on High Baby Watch Alert right now. Sorry I couldn't be there with you guys today to do this lesson in person, but family first. Is doing all right now. We actually went to the hospital, had to come back home because they said she wasn't quite ready yet. But like I said, we're on high alert. When the moment comes, we're going to be there. But let's do some related rates until then. Problem number one. At a given instant, the legs of a right triangle are 5 and 12. The short leg is increasing at a rate of 1 centimeter per second, and the long leg is decreasing at a rate of 2 centimeters per second. And I'm asking you, how fast is the hypotenuse changing? A couple things that you need to recognize already. Yes, we're talking about a 5, 12, 13 triangle. However, the distances are changing right now, so that means that we're going to have to deal with derivatives. It's not good enough to just have a squared plus b squared equals c squared. We actually need to do a derivative of that. Here we go. A squared plus b squared equals c squared. What we're going to try to evaluate is going to be dc dt. Is anybody bothered by the fact that I did a square root on both sides so far? Hopefully not. I was talking to somebody last week that said, I didn't realize that the distance formula and Pythagorean theorem were the same thing. Yes, they are. Now that you have this, we're going to go ahead and do a chain rule on it, differentiating with respect to time. That means we're going to have a dt on the bottom of every one of the derivatives that we do. This is what you should end up with. dc dt equals 1/2 of a squared plus b squared to the negative 1/2 times 2a dA dt plus 2b dB dt. And again, all of those are over dt because we're differentiating with respect to time right now. I did a chain rule by moving the power down to the front, subtracting 1 from it. Then the inside derivative is right there for you. At this point, I have a whole lot of information that I should go and plug in. I'm going to highlight it for you. The 5 and the 12, those are respectively A and B. The next couple of pieces of information that you need to be aware of. The short leg is increasing at 1, and the long leg is decreasing at 2. That's going to be these values. One of them is a positive 1, the other one is a negative 2. This is what it should look like once you substitute all those values in. And a handy dandy calculator is all you need to finish solving this thing. dc dt will be calculated using a calculator, and the main important thing that you need to make sure you put on here is centimeters per second. I'm going to pause my screen so I can turn off this teapot that I was making for Erica, and then we're going to move to the next question. So at the end of this problem, you ended up with a negative 1.462 centimeters per second. That says is that as this ladder is moving in each direction, the vertical and the horizontal direction, the hypotenuse is getting smaller. I think I've just said the word ladder. That's really not coming up until the next question. Here we go. All right, so 15-foot ladder is leaning up against the wall this time. So same idea as what we were talking about before. You got a wall. This ladder right here has to be 15, and that's super important. Top of the ladder is sliding down the wall at a rate of 2 feet per second, and I want to know how fast is the bottom moving when it's 12 feet away from the wall. Two major things are happening here. One, we have a Pythagorean theorem, but the second piece of this, and the more important thing, is I didn't actually give you all the values that you're going to plug in this time. Let's go ahead and start off with a squared plus b squared equals c squared. In this particular instance, I have given you the c value automatically. I know it has to be 15, so if I substitute that in, you're going to notice that there needs to be a relationship established between a squared and b squared. I'm going to have to do an extra step in this problem because of the substitution needed. There's a substitution in this problem because, one, I don't know the values for both a and b right now. I was only given this 12. I'm going to substitute that in. I'm going to use it in the letter b. A squared plus 12 squared is 144. That equals 225. That means that our a value is going to be 9. 3, 4, 5 triangle for those of you counting at home. This is actually super important again because we're going to need it once we go and do that derivative. Let's go ahead. I said a squared plus b squared equals c squared. And we established already that c squared is going to have to be the same value over and over and over again. It cannot change. So when I actually go and do the derivative of c squared, it's not possible. I have to keep it a constant value. It's going to be 0. I'm going to get 2a dA dt plus 2b dB dt. So what I'm going to be solving for in this particular instance is the missing variable. I'm going to plug in a 12 here for b. It's the base. The dB dt is what I'm going to be solving for. How fast is it moving away from the wall? When I am given the value of 9 for a and a value of -2 for dA dt. That's 2 feet per second in the vertical direction. Easy enough to solve. All I need to do to solve this one is get the dB dt all by itself. That is going to be a -36, or excuse me, a positive 36 over 24, which is going to reduce down such that dB dt equals 3/2 feet per second. Might as well go to the number 3. All you sports fans out there, let's talk about baseball for a second. Baseball, talking about a baseball diamond. It has the shape of a square. Sides are 90 feet long, no matter where home base is. So that means I'm looking at something that looks like this. All 90-degree angles in it. And this distance is 90 all the way around. So what I am giving you in this particular problem is that I'm giving you a distance where the player is 40 feet away from second base. He's about right here. That means there's 50. This is still 90. The next thing that I told you is that his rate, I'm going to call it dP dt. Why P? Because of player. The rate for this player is 28 feet per second. I've got some distances to consider already, and what I'm looking for is how fast is he getting away from home plate. Home plate this time is right here. This is the distance that we're trying to figure out. This is the rate of change that I am considered, the distance to home. We'll call it dH dt. H for home. Let's go ahead and do it. You know the formula's got to be a squared plus b squared equals c squared. And in this particular situation, I'm going to go ahead and change those variables to fit our purposes. We're going to use p squared for the player's distance, first base distance, I'm going to call it F, and then I'm going to call H the distance to home, just because I feel like it. I'm allowed to do that. It's completely okay. One of the variables here is fixed. We know that F is automatically going to be 90. It's never going to change. So dp dt is still present. If I go ahead and do this derivative, what you should recognize is that df dt is 0. It's not changing. And because it's not changing, I don't have to worry about it. It's going to cancel out that entire term. And on the other side, I get a 2h dh dt. Let us continue. Again, we said this is going to cancel out here. No need to keep it around anymore. I have 2p dp dt equals 2h dh dt. I can substitute in some values. 2 times 50 times 28 equals 2. I'm going to leave that blank for a second, and then dh dt. Right, so a second ago, I just left that blank space right there because you don't know what that value is yet. You need to go back and figure that out, and that's coming from your original a squared plus b squared equals c squared. We gave you the values of 90 and 50. You actually know this actual distance right here is supposed to be 102.956. And at that point, you can go ahead and plug it all in. You take the 2 times the 50 and the 28, divide it away by a 2 and a 102.956. You end up with dh dt. The distance from home plate is changing at a rate of 13.598 feet per second. All right, so I've only got time for one more quick one. It's going to take about 2 minutes. I'm going to pause my screen real quick so I can get it all set up for you. All right, so a spherical balloon is being inflated at a rate of 20 cubic feet per minute. The rate, or I'm asking you for the rate at which the radius is changing when the radius is 15 feet. Now, I know in the original question I asked you about surface area, but I'm not concerned about that for right now. Given our time constraints in this video, I don't have a chance to do that. I'm going to talk about the radius. In this particular situation, you need to recognize that volume is what I've given you, 4/3 pi r cubed. I'm going to take this value and use it in my derivative this time, plugging in all the necessary information. dv dt